Okay, so good morning, everybody. Thank you for the introduction. So as you see, today I would like to talk about some theoretical results connected to cold atoms. In particular, I will be talking about this process of molecule formation that will be put in the context in some recent experiments related to ferromagnetism in ultra-cold Fermi gas. But before I start talking about physics, I would like to mention that this work was done in the collaboration with, first of all, Andrzej Sylwik, who is now at Stockholm, and thanks to this online forum is with us today. Then Piotr Grochowski, who I guess since 2 or 3 weeks is in Barcelona. And of course, the whole research was guided by Professor Żążewski from Japan. Okay, so before I start talking about our research, I would like to briefly review the problem of ferromagnetism in ultra-cold gases. So we will be talking about some experimental results that, of course, are not mine. I'm just giving this as an inspiration to our theoretical investigation. And you have to know that I will be talking about a peculiar form of ferromagnetism that is kind of different than ferromagnetism related to, for example.
Is it only me who doesn't hear very well, or it is not very loud?
Not very loud, okay.
About other guys, do you hear very well?
Well, I hear it pretty well, but maybe Maciej, can you speak a bit louder?
A bit louder, okay, I will try.
That's good, thank you.
Okay, so we will be talking about so-called itinerant ferromagnetism that is different to local ferromagnetism that is somehow related to models like Ising or Heisenberg model. So in this case, the spins essentially can move. That's the main difference. So instead of spins localized on some lattice, the fermions, in most cases electrons, can move. And in order to really analyze the phase transition, you have to take the kinetic energy into account. Okay, so this kind of ferromagnetism is described with classical Stoner model. So if you consider a very cold gas of fermions, so let's say we are at T equal to 0, and you somehow modify the repulsive interactions. Of course, in the case of electrons, you cannot do that. You just you can play with the density of the electrons, but in the ultra-cold settings, you have Feshbach resonances, and you can tune the interactions. So let's say you increase the interactions, and for weak repulsive interactions, what you have is a paramagnetic state as a ground state. So you do not have any ferromagnetic domains. You do not have the symmetry breaking, and the overall magnetization of such a state is 0. And then what you do, you make the repulsion stronger, and what you see is the appearance of ferromagnetic domains, where you have atoms grouped into these domains where the spins are aligned along the same direction. And this corresponds to non-zero magnetization. Okay, so such a form of ferromagnetism is visible in, for example, iron or nickel, but due to the fact that you can easily play with interactions, people were trying to realize such a phenomenon also in ultra-cold gases. Okay, but there is one obstacle to do that, and basically that obstacle constitutes the main goal of our investigation. And what is that obstacle? So if you want to have Feshbach resonances in your system, then you have to pay a cost of having an interparticle potential that has a bound state. Okay, so this is different to Coulomb interactions, when Coulomb interactions are just purely repulsive interactions without a bound state. If you have a Feshbach resonance tuning in the system, as I cited here the experimental paper, there has to be underlying bound state in your interparticle interaction. So what you can expect is that spin ups and spin downs will form pairs bound by these interactions. And it turns out that this little feature drastically changes the ground state of the system, because you no longer can expect that you will have a symmetry breaking like here and ferromagnetic state in a ground state. What you expect as a ground state is just all spin ups and spin downs paired up. Okay, so this is very distant from any kind of domains. So the conclusion here is that in the ultracold settings, you cannot really look for ferromagnetism in a ground state. What people try to do is to look for some traces of the ferromagnetic behavior in excited states. Okay, so there is an ongoing research. People try to realize that ferromagnetic transition, and the first experimental results I would like to talk about is the experiment from MIT, some group of Wolfgang Ketterle. So they took a simple mean field theory Stoner model, in which they get a bunch of measurable quantities that display discontinuity at the phase transition. So first of all, you get that you have a distinguished interaction for which the non-zero magnetization appears. And of course, there are different quantities, as always in case of the phase transition, that display discontinuity. And they were able to look not at the magnetization, but at the kinetic energy. So the second plot here. And what they observed that if you start with some high temperature and you lower down the temperature to the level of a very small temperature in comparison to Fermi temperature, then you see some kind of signs of a phase transition. It's some kind of discontinuity of derivative of that kinetic energy.
Maciek, somehow I don't see the bottom part of the slide. Like,
okay, so
is it only me?
Maybe.
No, we all don't see it.
It's universal. Also, earlier slides were cut.
Okay. So I'm going into full screen mode.
Full screen.
Okay.
Oh.
Full screen. Yeah.
And afterwards, share.
Yeah, but
Right now?
Yes.
Oh,
Now
it's okay?
yeah.
Yes.
Okay, sorry for that. So here we see this shaded area that corresponds to value of interaction for which we have a, let's say, phase transition. That's the only, let's say, evidence from that experiment on the level of these observables. But there was another thing that they were able to measure, namely the atom loss rate. Okay, so as I said, in such a systems, you may expect that the spin ups and spin downs will form molecules. And if you consider, for example, the paramagnetic state, so on the left of the gray box, then, okay, so I have to, let me, because I have to turn on the, okay, now it's fine. So if you are on the left side of the gray box, then we are on the paramagnetic state. All atoms are mixed, and it's kind of easy for molecules to be formed, okay? Because there is a lot of room for spin ups and spin downs to meet, and the atom loss rate that corresponds to this molecule formation, because if the molecule is formed, then the resulting energy structure is different, and your atom, the anti-auroral light that detects the atoms does not see it, and this effectively corresponds to the loss of atoms. And in the paramagnetic state, it's relatively big. And then if we are on the left-hand side on the right-hand side of this gray box, we are on the ferromagnetic side. So the situation is kind of different because we have now domains. Okay. And the only place where the pairing may take place is the domain wall. Okay. So the chance of spin up and spin down forming a molecule is lower than in the paramagnetic state. So this kind of, this is another form of evidence for the ferromagnetic phase transition. Okay, so that was the first experiment. It wasn't very clear and conclusive, and people tried to somehow ease their life and prepare an artificial experiment and to check whether these domains are stable at all. So what they did, they prepared two domains in a harmonic trap. So let's say here we have spin ups, and here we have spin downs. Okay, here we have trapping that pushes the gas towards the bottom of the trap. And initially these domains were separated with a high potential barrier. Okay, so everybody can agree that in the initial state we have two domains, and we consider very strongly repulsive interactions. And at time equal to 0, we just switch off that potential barrier in the middle and see what happens, whether this will mix or stay separated. This experiment was kind of designed to check if the domains can be stable. And what you see as the time goes on, that these clouds meet at the bottom of the trap. We have a minimal distance between these clouds, and after that they bounce back and return to the initial state. They do not mix. Okay, so we can say that we have a stable ferromagnetic phase because such a state corresponds to non-zero magnetization. The domains are stable, and you can look at the position of center of the mass of the respective clouds, and you see some oscillations. And after some time, the oscillations, of course, decay, and everything is mixed up at the bottom of the trap.
Maciej, could I interrupt with a small remark?
Yes.
Of course, historically, everything started with a real magnetism. But here, when you say about ferromagnetic state, it's not really, it has nothing to do with magnetic field, right? It is just two kinds of atoms, fermionic atoms, that are either separated or not, rather than formation of some magnetic dipoles.
Yeah, of course.
Okay, go ahead.
Yeah, and this experiment was, there was some research about this experiment done here in Warsaw and also in Białystok. So there was a paper in 2016 addressing the statics of such a system. Then 1 year later, the dynamics. So for example, the frequencies governing that motion, and recently dynamics with taking into account the finite temperature effects. Okay, so this was a regime of very strong repulsive interactions, basically unitary regime of infinite Poisson. And one can ask whether you can stabilize the system with finite interactions, finite repulsive interactions. Okay, there was an experiment in 2017 in which they were looking at the magnetization. The magnetization is, of course, equal to 1 if we have a ferromagnetic perfectly separated state, and it drops down to 0 when we go to the paramagnetic phase. And if you look at the plot of magnetization as a function of time, then you see that one can find the value of a repulsion for which this magnetization exhibits a plateau. Okay, so there is finite time when we have large magnetization. After that time, the magnetization drops to 0. And one can ask, what is the reason for the instability? Why this plateau? Why this magnetization goes to 0 after some time? And this is now a topic of, I would say, a debate. People were trying to understand that instability via dimer formation on the domain wall. And okay, so these are the experiments that I somehow given as an inspiration for our research. So I hope you see that the problem of the performation on the domain wall is kind of important problem for ferromagnetism in ultra-cold gases. And our goal was to somehow consider a minimal model of such a process. So we considered one dimension, first of all, one-dimensional harmonic trap. We cannot go up because of the computational complexity. So to be precise, we consider one-dimensional harmonic trap. Here we have M up fermions. Here we have M down fermions, the other species. And initially, the whole system is separated with a barrier. Okay. And what we want to consider really is to consider a system with repulsive interparticle potential, but at the same, we want this potential to host a bound state. So you may say that we want a potential that has a strong short-range repulsion and weak long-range attraction. So at short distances, the atoms will repel, but at the same time, we will have a room for the bound state formation. And what we want to check is to just remove the barrier and see how the system evolves. And for that, we really want to restrict ourselves to full many-body dynamics. So no effective classical or master equation approaches. We just want a unitary evolution of small system. And in order to get this full many-body dynamics, for the modest case of 1 + 1, we have analytical solution to the problem. And for 3 + 3 and 2 + 2, we use numerical methods such as DBP. Okay. And we want to ask basically two questions about this system. The first one is just to observe behavior of the clouds. So do the components mix and form a paramagnetic state, or stay separated and we have a ferromagnet? That's the first basic question. And the second one, perhaps more interesting, is the question regarding the presence of pairs, dimers being formed in the system. Okay, so we want to address the question, what happens if our potential has a bound state? Can we really say if we have molecules in our system, and how to check that? How to formulate the theoretical observables that would give us the answer to the presence of the molecules in the system. Okay, so we need, before I go to the problem with the bound state, I would like to give a short recap of all the results. So what happened to give you some set up a stage and give you some idea how the system behaves. So we consider now a simple contact interactions, repulsive contact interactions, and let's say we take two regimes. First regime corresponds to the paramagnet, weak interactions, and the second one will be corresponding to strong interactions. Let's see what happens. If we have a paramagnet, then as you see, the particles either are, the two clouds either overlap or switch places. And if you take a time average of such a behavior, then you end up with zero magnetization, and this is a paramagnetic state. In contrast to that, we have ferromagnetic behavior stabilized via strong repulsion, where the two clouds stay on the respective halves of the harmonic trap. Nothing. We do not have mixing in the system. This is our ferromagnetic point of reference, this little movie. But we want to go beyond that. We would like to somehow study the process of molecule formation. So for sure, we need a different potential, but also we have to somehow answer the question how to relate such a processes that we somehow imagine classically to full many-body wave function. So we'll have to build some understanding what are the proper observables and how to connect our presuppositions about molecule formation, how to connect them with a full many-body wave function. That's our goal. Okay, but first we start with the potential that we employ to study this molecule formation. So the minimal model of potential, again, the minimal model of the potential is we propose the free delta potential. Okay, so instead of just one delta, you have also two additional delta that act as a weak attraction. So this potential has three parameters. C0 corresponds to strength of zero range at repulsion. CL corresponds to the strength of long range attraction, and L is the characteristic length scale of the potential. And of course, one would like to have rather something like that corresponds to Lennard-Jones potential or something like this. But due to the fact that our numerical methods are much better in the case of free delta potential, we employ the free delta potential, and at the same time, you can solve that free delta potential exactly. And basically, this model really captures the most important physics that we want to describe. So we have the strong repulsion, we have the weak attraction, and what's more, this parameter L can be easily understood as a dimer size, or characteristic size connected to a dimer, because you can think that if the molecule is forward, it looks like this. So you have one atom there, here, and one spin down here, or vice versa. Okay, so this L is characteristic size of the molecule that we expect to appear in our system. Okay, so we have the interactions, and now we have to somehow start dealing with that problem of molecule in quantum mechanics. So let's start with a two-body problem. So consider just two particles. Then you can, of course, introduce center of mass variable and relative variable and split the Hamiltonian into two parts. And one may ask the question how the wave function that would correspond to a really molecule may look like. So I will give you a proposition of the wave function, and we will decide whether it is good or not just by looking at its evolution, at its time behavior. So my proposition is to take a product of two functions, where the first function f describes the motion of the center of the mass of the molecule, and it is an arbitrary function of Cm. We do not specify it. And the phi, describing the relative coordinate, is an eigenstate of relative Hamiltonian. Okay, and if you consider now the time evolution of such a two-body wave function, then the first part, the center of mass degree of freedom, evolves non-trivially. Okay, the molecule moves, but the relative degree of freedom evolves trivially because it is an eigenstate of relative Hamiltonian. Okay, so such a wave function, if you consider an evolution of such a wave function, nothing happens in the relative degree of freedom. It is frozen out. So this is something that you would expect from molecule, yes, because then center of mass moves, but nothing happens when it comes to the relative coordinate, relative distance between molecules. Okay, in particular, the probability distribution of relative distances between particles does not change. And in order to have the possibility for such a wave function to exist, the relative Hamiltonian must have localized eigenstates. So we need bound state with negative energies. And this is not always the case, because if you have the purely repulsive interactions, you do not have such localized eigenstates. You really need some attractive part of the interparticle interaction. So if we apply this analysis to free delta potential, so we just look for eigenstate of relative Hamiltonian, then we can do that analytically. We may formulate an equation and say that the relative Hamiltonian has a localized eigenstate if a certain equation has a positive solution. And if it does, then you may plot this corresponding relative wave functions. And what you see that these wave functions have a node at relative distance being equal to 0. And this is because we consider free delta potential with a very strong repulsive interactions. Okay, that prevents particle from being at the same position. But you have an enhancement of this wave function at the position given by the distances between deltas. And this is because the second particle basically localizes at the distance given by the L. And now you can make a plot of the parameters. So here you have these parameters U that combine the parameters of free delta potential. And you may prepare the plot for which you just mark the values of parameters where the bound state, where the potential has a bound state. Okay, and we are interested only in the we expect the molecules to appear only if our potential has parameters belonging to that shaded area. And in particular, if you look at this plot, then there is a critical value of UL, okay, for which the UL corresponds to the finite range attraction. And if you have attraction stronger than UL, then the bound state exists no matter how strong the short range repulsion is. Okay, so as we will be working in the regime of very strong repulsion, then we want UL to be greater than this critical value. And this corresponds to some particular value of coupling C. Okay, and this is very important value of our interaction potential. And if this coupling will be greater than this critical, we expect the molecules to be formed in our system. Okay, so this is really important value of parameter. And you can find this is analysis basing on two-body Schrödinger equation, but you can employ some variational methods to describe the ground state of such a system. This variational method is called Allow-Cifau. I don't want to go into much detail here, but this method says that exactly for the same value of critical, the same value of attractive coupling, something happens in the ground state. Okay, so this is many-body. It's not only two molecules, but two particles. This is a many-body analysis, and it gives the same critical value. Okay, so before I will describe the observables, let me just give you an observation from classical physics. So if we want to study the molecule formation, we need more than two particles, because the process of just, if we were considering the process of two fermions transformed into one dimer, this is prohibited via conservation. This cannot happen, because of that, we expect that dimers cannot be formed in 1+1 system. Okay. To sum up, we would like to observe the signs of molecule formation when two conditions are fulfilled. The first one will be corresponding to the presence of the bound state, and this may be conveniently represented by the need of sufficiently large attraction strength. Okay, this is the first condition. And the second one is we need at least 3 particles in our system. So in 1+1, we do not expect molecule formation. And now we have to somehow deal with these observables. So our calculations gives us full many-body wave function. But of course, if we want to study pairing, it is somehow sufficient to restrict yourself to two-body correlations. And because of that, we consider density correlation function. So in order to get this density correlation function, you take the modulus squared of the wave function, you integrate out all the degrees of freedom, but the first coordinate of one spin-up particle and the one coordinate of spin-down particle. And it's important what is the interpretation of that function. Okay, so it has a probabilistic interpretation. Its value at a given point, xy, gives you the probability density of finding up particle at the position x and down particle at the position y. Okay, so the two-body correlation, two particle correlations are captured by this function. And now, during our investigations, we were thinking about this problem, how to detect the molecules, and one can come up with a classical, let's say, thought experiment that would give you a nice distinction between a gas where you have no molecules and a gas when some molecules are present. So consider a classical gas and imagine that you take a photo of that gas, you just write down the positions of all particles. And what you do next is you calculate the relative distances between these particles. And you make a histogram. These positions are well defined. This is a classical gas. And you make a histogram. And what you see in the case without a gas, without molecules, it's just some smooth probability, just smooth distribution related to temperature, etc. The situation will be a little bit different if we had a gas with molecules, because then you have a non-zero fraction of molecules that really like to stay in a characteristic distance, okay, equal to L, that gives you the dimer size. And what you expect from such a histogram, it should have a local maximum near that point. And this is kind of sign of molecules. That's the difference between two cases with molecules and without molecules. That we, in the case of classical gas. And now we want something equivalent to this in quantum mechanics. So in quantum mechanics, you can just get a probability distribution of relative distances between particles. For short notation, let's call it per distribution function G. And again, it is important to know it's probabilistic interpretation. So its value at given point R gives you probability density of finding two particles at the opposite spin at the distance R. Okay. And the last observable that we will use to study the behavior of the clouds is the single particle densities, one-body correlations. This is exactly the observable that I was showing you in these movies. Okay, it's nice to see what happens in the system.
Maciej, speak up a little.
Okay, speak up. Okay, so stability of the maze. So we keep a very strong repulsion. We have fixed distances between deltas, and we modify the attraction. Okay, and here we have two cases. First one is M equal to 1, so 1 + 1 molecules, and there we have 3 + 3 molecules. And we start with the case of zero repulsion, zero attraction, just single repulsive delta, just I showed you at the beginning. And what you see is stabilization of the clouds. Just as it was, we have very strong repulsive interactions. This is nothing surprising. The more interesting things appear when we are close to the critical value of the attraction. So in the case of M equal to 1, we see that we have a paramagnet. So the clouds mix. We do not have non-zero magnetization. This average out to 0 over time. On the other hand, when M equal to 3, the system is stable. It's ferromagnetic. So we remember that in this case, we do not have molecule formation. Here we have. So one may conjecture that in M equal to 3 case, these molecules are being formed, and these molecules somehow stabilize our system. Okay. And what is really surprising is that if we have very strong attraction, okay, so we have strong repulsion and also strong attraction, then the system is again stable. Okay, this is really strange, really surprising. And I don't want to go into much detail about this strange behavior. So it turned out that it is more general, and we decided to prepare another paper about this behavior. I will just briefly tell you how this works, or what happens in such a situation. So it turns out that you can, if you take the 1 + 1 system, you can of course solve it analytically. And for our initial state, you can see from our exact solutions, then the evolution under Hamiltonian with very strong repulsion and very strong attraction is the same as the evolution under Hamiltonian with very strong repulsion and some kind of strange potential that corresponds to very strong repulsion. Okay, so these are totally different potential, but at the same time, they give the same evolution. So this is really strange behavior. We still investigating this. I will be talking about this next week and at the PEC seminar. So if this duality kind of seems interesting to you, feel invited to listen about this. Okay. So we suspect that it holds also for larger systems, and for sufficiently strong attractive interactions, the domains are stable, but also the pairing processes are suppressed. So we expect that the pairing process, we do not have pairing for sufficiently strong attraction. Okay. And now comes perhaps the most important slide of the whole talk, in which I will try to argue for the presence of the molecules in our system. So there is a lot of information here, but let me go through it carefully. Okay, so let's focus first on these black boxes, black squares. Here we have first column corresponds to m equal 1 system, so 1 plus 1 particles. The second one corresponds to 3 plus 3. And what we see here is the density correlation function averaged over time, over 5 periods of the trap. So you may think that these pictures represent the average two-body correlations in our system. And the first thing that we may note is that in accordance to what I said about the 1 plus 1 system, it is not stable around this critical point. Because if you want to have a stable system, then the whole picture must be non-zero only below the anti-diagonal. Okay, this is the case for 3 plus 3. On the other hand, when we have 1 plus 1 around the critical value of the attractive interactions, I mean here B, C, D pictures, then we have a non-zero part above the anti-diagonal, and this corresponds to instability in the system. Okay, this is first observation. And now let us focus on this row. This row corresponds to the critical point. And let us take a look at the picture H that corresponds to 3 plus 3. And let us observe that we have a very peculiar trail. We call that banana in our investigation. So this trail corresponds to the line x minus y equal to L. Okay, so this says that there is a large probability of having two particles of opposite spins at the distance that is roughly the distance, the shape of the molecule. So this really tells us that we have a molecules in our system, and we see that for the critical value interactions, and slightly stronger attractive interactions, and we do not see that in strongly attractive regime. In 1 plus 1, we do not see such a trail because, okay, we see something, but it is not a maximum of the whole distribution as it is in the case 3 plus 3. Okay, so we are done with these black boxes. Now let's move to the third column. And in the third column, we have this distribution G of R as a function of time. So we see spatiotemporal plots. So for each time we have the distribution, and maybe let us just simply focus on the case of critical value. So the picture M. So you see that when we look at the G of L, this corresponds to this bright line, and the bright line tells you that this distribution roughly looks like this, that you have a maximum for a distance L, and something happens there. So this is very close to that histogram that I was showing you. Okay, so this is kind of another evidence for molecules being formed in our system. And if you look at the m equal to 1, where we do not have molecules, the situation is kind of different because you have a maxima, but these maxima oscillate in time. And these maxima do not correspond to the fraction of molecules that reside at the bottom of the trap. It just means that these molecules oscillate, meet each other at the bottom of the trap, but due to oscillations, we cannot really say that we have a fraction of molecules that resides there and is somehow stable in time. Okay, so what we may say something more about this molecule formation. So we may somehow estimate the number of molecules that we have in the system. So in order to do that, we have to calculate the expectation value of the number of pairs of size L. And to get that, we go to this pair distribution function. And this, of course, is a function of time. We may average it over, let's say, 5 periods of trap. And here are presented the results for 3 cases, n equal to 1, n equal to 2, and n equal to 3. So what you see is that for very weak, for the case when you do not have this attraction, we have almost 0 molecules. Then as we increase the attraction, the number of molecules goes up. It has a maximum around this critical point. And then it drops down. And it drops down because of that really strange behavior of strong attractive potential. Okay. And the another important thing is that there is these curves for m equal to 1 and m equal to 2, 3 split up. And we do not, and they split up because for m equal to 1, we do not expect the molecular formation in the system. And the interesting thing is that for m equal to 2 and m equal to 3, you get the same number of molecules. And yeah, I will try to resolve this in a moment. Okay, the next thing that you may look is a spatial distribution of these molecules. So you may ask the questions, okay, we have molecules formed in the system. Where are they? So in order to somehow answer that question, you may formulate a distribution K that tells you what is the distribution of these two-body correlations across the trap. And you see here plotted for m equal to 3 that the molecules are mostly at the center of the trap. And this corresponds to, because here we have one cloud, there is the second one. And this corresponds to this domain wall. Okay. And now this is 1D. So this region is very small. And you may argue that, okay, molecules can be formed only here. What happens if I increase the number of particles? Now, then this region, which is essentially a point in 1D, does not grow. Okay, so because of that, we may add some up and down atoms, but the region where the molecule formation takes place does not grow. Because of that, the number of molecules does not grow with m, because the region is always the nice spot where the molecules may be formed is always the same, regardless of the size of our system. This is a peculiar from 1D because in 2D the place when the molecules are formed would be just a line. In 3D this would be some kind of a surface. In 1D you can describe, you can somehow explain this behavior because with the
Maciej, but also in 2 and 3 dimensions, it's of course bigger region, but it's also independent of the total number of atoms.
The region?
Sure.
Why? Because the clouds grow because of the
right.
So the regions should grow.
Ah, that's what you have in mind.
The contact.
Yes. Okay, I agree.
Okay. So yeah, that's basically all that I would like to say. So we have some arguments for the molecule formation. Let me just go now to the conclusions. So the first observation is the observation related to the Stoner model is that you can, with the strong repulsive interactions, you can stabilize 2 domains of a Fermi gas. Okay, that's not a very surprising thing. The next thing is that indeed is surprising, is that you can, with a strong attractive interactions, you can also have a stable system. Okay, so you can have a very strongly attractive system at the same time these 2 components don't mix. And we check that both with analytical solutions in case of 1+1 and numerically in larger systems. And for 2+2 and 3+3, we observe signs of molecule formation in the system, provided the long-range attraction is stronger than some critical value. Okay? If you increase that value of attraction above some certain threshold value, the pairing in the system is suppressed, and this is in agreement with the previous point that strong attractive interactions stabilize the domains. And you may say that these molecules concentrated near the domain wall enhance the stability of the ferromagnetic domains. That was the point that I've made during the discussion of the stability of the clouds. And the last thing regards the classical physics. So in 1+1 systems, the dimers are not formed. So our quantum mechanical understanding is somehow aligned with the classical conservation laws. Okay. So thank you very much. So now, if you have some comments or questions, I'm ready to answer it. Thank you.
Okay, thank you very much for your talk. And now we have time for some questions. Please go ahead.